Coming up on today's podcast.
You don't have to be a video game fan. You don't have to like a certain fixed aesthetic that's forced upon you by the hardware. You don't have to like that in order to enjoy a video game anymore. And I think that's one of the reasons that there's been such an explosion in popularity, because it's become a little bit more like being immersed in a movie. And that's something that they always wanted. The cover art on video games always wanted you to think that you were about to be immersed in a real-time movie of your own making. There's something to say here about this takes us all back to our film and TV route, is that a recent release of Aliens, the James Cameron 1986 release, I think it was shot in 85, and they haven't rescanned it. AI upscaled it from a high-def transfer from some time ago, which has led to people having extra eyeballs and sideways ears and all kinds of unpleasantness. That's where it can go wrong.
Hello and welcome to How to Understand Today, your regular insight into the wheres and wherefores of the world of technology, with me, Simon Wyndham.
I'm Dave Shapton.
I'm Phil Rhodes.
And today we're going to be discussing the technology of gaming. Games have long been a driver of technological development, with the existence of GPUs being a primary example of technology that wouldn't exist without teenagers twiddling their thumbs in their bedrooms. These days, of course, games are a massive industry, and unlike the days when I was playing Stunt Car Racer on my Atari ST, they're now seen as a cool thing to do, even a social thing. So, Phil, back in the day, you, I believe, were an Amiga user, but the history of gaming goes way back further than that. Can you tell us a bit of history as to how important the development of games is when it relates to the advancement of general computer technology?
Well, sure. I mean, the thing about this is that the GPUs that we have now, which, mind you, are crucial not only to video games, but also things like AI, little things like that. That is a development that arises pretty directly from a through line of technology that goes back to the late 70s, at least. We had Amigas back in the day, but that was nowhere near the beginning of it. I mean, they were derived to some extent from other Commodores, other work on C64s, which came off long since the original home computers were things with switches on the front. And it was pretty quickly realized that if you have a computer, you probably want some way to talk to it. If you bought perhaps the first common home computer was an Altair 8800. It's the one it looks like a sort of 19-inch rack with a bunch of switches on the front and LEDs. If you had one of those, there was no video display on that at all. It just had a bunch of switches and some LEDs. You could connect up a serial terminal to it. But most of the early stuff, if you could plug in, once you get past the Altair series, if you could plug in a monitor, one of the problems it had was that the CPU in this thing would spend half its time drawing the video display. And this was certainly the case with a lot of the early Sinclair stuff, which had a little ZLED CPU. And you can always tell because if the ZLED CPU is clocked at 3.5 something megahertz, you can tell because that's part of the timing for the video display. And it's one of the reasons that video games sometimes ran faster when you ran them in the United States, because the frame rates were higher. You clocked the CPU faster. It was pretty quickly realized that when you've got this incredibly expensive CPU in there that you want to do work, you don't want it to spend literally half its time sometimes drawing video display. And they quickly started developing chips that would do simple things like plot text to the display, potentially while the CPU was doing something else. So that's where GPUs come from. You can argue, there's different companies and different levels of technology involved, but you can argue that what we have now in GPUs derives from people putting chips in very simple, very elementary home computers to do the video display, so the CPU didn't have to. And that comes all the way up through Commodores and the VIC-20s and the VIC chip, with Amigas had, they had all the Amiga custom chips had girls' names, but they had chips in them to do sprite rasterization and color changes and things. Then in the late 90s, you start seeing, or mid to late 90s, you start seeing companies like 3DFX. And then the PlayStation pops up with its somewhat elementary, but, effective enough 3D. Then you see places like NVIDIA start to compete with it, and here we are. That's roughly what the history of it is. You can argue about exactly what derived from what and in what way, but if there had not been, let's say, a Commodore 64 with what it had, there probably wouldn't be an RTX 5000 series now.
I'm astounded at how quickly these specialized chips have developed, because I remember when GPUs first came out and we started to see, advanced sort of texture mapping on 3D objects. Um, the talk was that there would never be enough computing power to be able to do ray tracing in real time. That was just something that was completely and utterly just way out there. But now, we see specialized chips which deal with real time ray tracing, which I still find amazing.
I think you make a good point, Simon. I mean, ray tracing, it's almost like the Turing test, which is the test to determine whether a computer can pretend to be a human being, and we've kind of sailed past that point with AI, and actually we've sailed past the point where ray tracing, just to explain it, is also called path tracing sometimes, I think, but essentially it mimics the way light behaves in the real world. In the real world, light bounces off things, and it bounces off things differently. Some things it will bounce off in several directions. That's a diffuse surface. Others, like a smooth, shiny surface, it will bounce off in a predictable way. But almost every scene, every room, every environment is a mixture of these kinds of surfaces. And the only way to make something look photorealistic in all circumstances in a game, because don't forget, games are interactive. They don't have a fixed timeline. So the only way you can get this photorealism in a made-up 3D environment is to simulate the way light behaves. And to do that, you effectively have to trace every ray of light through each of its bounces and reflections, and then work out what the scene would look like from your point of view. So saying from your point of view, that is the first way in which you cut down the amount of data, because you only have to work it out from your point of view. And many other ways, like hidden object removal and so on, to cut down the amount of calculation. But nevertheless, it is a massively processing intensive job.
Yeah.
And just was it 5 years ago? Something like that. We started to be able to do that on a GPU that you could buy off the shelf and plug it into your reasonably powerful computer.
Yeah. And it's even more incredible when you take into account developments like Unreal Engine, where when Unreal Engine 5 first came out, they did a demo of I think it was a mountain scene, and this there were it looked like rock textures which you would normally associate with texture mapping, whereby you take basically an image and then slap that onto a very simple 3D object, and it makes it look more complicated than it actually is. But this was doing each individual the texture was made up of millions upon millions of polygons, which is again astounding when you think of the calculations involved. So Phil, where do you see this all going? I mean, we can't have, how can we have infinite increases in the processing technology that GPUs will be able to give us? I mean, where can this end?
Well, it's kind of interesting because we just hit the point now where, until fairly recently, what people were trying to do was to render more polygons so that things didn't look like they were made out of a huge number of triangles. So, you make the triangles small enough you don't see them, fine. We were pushing for more resolution, more frame rate, more texture memory, all that kind of stuff. And that's all great. But we hit the point, as we have in so many other parts. I mean, we're all people who've got a background in film and TV, and film and TV technology has sort of hit a sensibility barrier beyond which we don't actually need much more of it. And the issues with video gaming were that the amount of effort required to generate the world, which is at this point still fairly manual task, was more than you couldn't reasonably, for what you can make out of making a video game, you can't reasonably spend enough effort to tax the graphics card with all this detail you want to display. You can make simple scenes, the demos are always small scenes with very high resolution content, but you can't make a whole video game like that. So saying we need more rendering capacity on the graphics card wasn't useful. Now, of course, these things are now not just graphics cards; they're general purpose processing units. They're a coprocessor, as we would have said back in the day. And it's kind of almost come full circle in as much as we don't necessarily want to render any high resolution because we can already render 4K, which is more than adequate for most applications. And even then, what people have realized is that if you want more than 4K, or even if you want 4K, you can render high def, then use an AI upscaler in real time, which is still running on the GPU, but which isn't quite rendering a scene in the same way that they always were rendered. And what we might see is AI renderers, which might not be quite ray traced. They might not be quite scan lined as the non-ray traced sort of stuff that long has been. They might be a sort of hybrid or none of the above, where you train an AI to take a representation of a scene in a camera position and give you the picture. That's in terms of graphics rendering. And I think that's interesting because the graphics rendering part of GPUs has become, like I say, kind of a wash in terms of its original application in video games. As to where the amount of capacity of these things goes, one of the things that stops them being more performant than they are quite often is memory. Particularly now, we're starting to see issues with if you want to run a decent chatbot. I mean, no one's running GPT on the latest GPT on a home computer. But if you want to run decent chatbot models, or if you want to run a decent image renderer quickly, you need enough memory on the board to hold the entire model on the GPU at once. Otherwise, you cripple the performance. It's swapping it in and out to system memory. You might see more stuff coming up with more memory on it, which is actually going to be a boon to people running things like Resolve, because the color grading system Resolve eats graphics memory for breakfast. So that's actually a boon to everyone. You'll see more memory. And yes, you'll probably see more of what people like NVIDIA are calling tensor cores, because that's why somebody would buy a new one. Because at the moment, if you're a video gamer, you've got a 4000 series, you're fine,
Yeah. So you spoke about upscaling, and I know that the forthcoming Switch 2, I believe, uses NVIDIA Tensor technology. Is it DLSS technology, so that it renders it at a lower resolution, but upscales it to 4K, so it reduces the processing overhead.
Well, yeah, and it's interesting that you think that reducing the processing overhead by doing an AI upscale is less processor than just rendering a high resolution image to begin with, which is just bananas.
That's really surprising, because that, to me, is, in terms of my intuition as to what will be possible, that's several orders of magnitude out. You're used to kind of generative AI taking a long time, and obviously this would be highly optimized. But if it's able to do that, it's not a huge step, conceptually at least, to talk about AI video codecs, AI video compressors.
Yes. Sure.
And if that can be made to run efficiently, a fascinating thing once we get into that domain is that if you imagine, we're talking about up-resing. Well, let's imagine you've got a pretty low resolution picture and you use AI to up-res it. Where is that detail coming from? It's coming from what the AI algorithm thinks it ought to look like. And most of the time, it's pretty good. But Simon, I remember you did a little experiment where we had, I think, our first podcast. It was really badly lit. Either that or my face looks a bit like a pink chamois leather. But it didn't look great. And just an experiment, you up-resed it. And actually, anyone who didn't know me would think, oh, that's absolutely brilliant. That's so sharp. You can even see the stitching on his shirt collar. But anyone who does know me would say, that's not Dave. No. That's an imposter.
But it was that was using a specific new model that Topaz had developed, which takes it can basically reinterpret the image, and you can tell it to be more or less creative. And when you ramp the creativity up, it gives you an interpretation of what it's an interpretation of you.
There's something to say here about this takes us all back to our film and TV route is that a recent release of Aliens, the James Cameron 1986 release, I think it was shot in 85, released in 86. And they haven't rescanned it. They've AI upscaled it from a high def transfer from some time ago, which has led to people having extra eyeballs and sideways ears and all kinds of unpleasantness. That's where it can go wrong. I think when you're talking about something like DLSS, I'm not aware of what the internal details are. I suspect that's probably considered quite proprietary. But it reminds me of something that a company called vNova has been up to, whereby they've been writing a codec specifically to deal with kind of the resolution difference. I'm cruelly abbreviating it here, but it's kind of they're encoding the differences between a high-def picture and a 4K picture. And if you actually look at what those differences are, they're just lines and dots. If you isolate those differences, you end up with a white screen full of little black and coloured squiggles and dots and things, most of which are the size of a single 4K pixel. They're very, very fine. So you think, well, it's an amazing thing to do, but yes, if you think about it, it's not generating, and it's a mistake to say it's not complicated, but the output that it's required to create to convincingly upscale high def to 4K is a series of little squiggles and dots. So you're not really saying, I need you to understand, you as an AI, I don't need you to understand what the scene represents. I'm looking for the sharp edges. And that's where you start inadvertently generating sideways ears, because it doesn't have a full understanding of what the scene is. If I stand for anything in this debate, it's about making sure we understand what AI can't do. And I think that's important.
And with the new features in Premiere Pro, the editing system, which introduces that AI expansion facility that you find in Photoshop, but brings it to video, which for people who don't know, in Photoshop, you can take an image that is a certain size, and if, for example, you need the picture to be wider, you can expand the image, and then Photoshop will go look at the picture and go, and it'll introduce an AI generated extra piece of the image to fill in the gaps. And Premiere Pro now does this for video, which means you could potentially, for low budget filmmakers, you could film on a smaller set, I guess, and you could virtually expand your set with AI, which could be quite useful in that kind of sphere. But going back in history, games have a very close connection to films. At one time, games were obviously influenced a lot by the movies. Now it seems to be the other way around. But games have been a driver of a lot of this technology, simply because of their popularity, haven't they? I mean, going right back, we wouldn't have the power of computers that we have today without games.
I think it's worth looking at. We talk about these things getting more and more powerful all the time, but it's worth just looking at the timeline. And again, it's very easy to talk about things being exponential. It's almost like the word awesome. It's like everything is awesome. If somebody in a shop gives you some change, it's like, that's awesome. So the word exponential is a bit tired. It's a bit overused, but it does have a specific meaning, which is that something is multiplicative. Things multiply as opposed to add.
I mean, I just it's related to the idea of the getting more and more power. Back when we had the much more simplistic computers, programmers were usually using assembly language to get the absolute most they could get out of those computer systems. And you had the Atari ST and the Falcon 030, which was not very popular at all, but it had a DSP chip that was designed for floating point calculations, but somehow programmers made it work to do complicated graphics computations, and therefore the computer was capable of doing much more than it was on paper supposed to be able to do. Now, I remember when the PlayStation 2 came out, there was quite a bit of discussion in the games development world about whether or not the people who make these games and program these games could actually fully utilize all of the technology within that console, because it was so capable but it was so complicated to program for. And I wonder if that's the case now for some of these consoles and GPUs. Is it the case that, okay, we can keep increasing the power, but could the programmers really, if they really delved into it and made things as efficient as possible, get much more out of them?
It's always a multi-layered thing. You could always write in assembly language. You can move bits and bytes and blocks around at a very, very low level. It takes ages, but it's phenomenally fast. But it's equally slow to develop, and most commercial games would never get there. So one of the master strokes, people wonder why Nvidia was a $3 trillion company until DeepSeek, the Chinese AI program, came out and took a chunk of that value away. But it's one of the tricks they've got up their sleeve is this programming framework called CUDA, CUDA. And that allows you to write in a relatively high-level language some pretty powerful low-level stuff. And it's a common thread across most of their products, and it's allowed them to quickly build a powerful ecosystem of specialized products on the same platform, on the same substrate. And that's a kind of masterstroke. But when you're looking at the power of these things, the early microcomputers were so feeble in today's terms that the only way you could get any sort of performance out of them was to code in they call it close to the metal, without using high level languages like C++, Java, and Python and so on. So these modern languages are phenomenally productive, but they're also pretty inefficient compared to what you could do. So this highlights a theme that is going to go on for ages. If we suddenly stopped developing hardware at today's state of the art, I suspect that software would keep improving for 5 or 10 years, just through, optimization, building it better, but also you go to lower and lower levels in relation to the hardware.
Well, I know that, the console development in general has slowed down. It used to be you'd have a new console, quite regularly, but now they go quite a few years before the next version comes out.
There's something to be said about, software development, which applies not only to GPU stuff, but almost to pretty much everything else. The thing that's changed, and I think this is one of the things that the open source community needs to think about in the way it politically approaches this sort of idealized approach to software development, is that back in the early days, before any of this GPU stuff existed or anything even vaguely competent existed really, one person could write enough code to fill up a computer reasonably on one project, and that would be a single person's work. Now there's very little in the modern world that you could develop solo, which is why the open source community has endless numbers of text editors, but there is no free open source really competent nonlinear video editor. You can run Resolve on Linux, but it's not open source. You can run Lightworks on Linux, but it's not open source. And there's a couple called Sinulera and KDEN Live, or however you pronounce it. They help themselves enormously by calling things utterly impronounceable or downright offensive names. So the open source community doesn't do them any favors by giving them their products odd names, their software odd names, but you can't write a nonlinear video editor as a single person's project. I mean, you possibly could, but you'd be perpetually chasing the state of the art in terms of feature set because you'd never get anything done. And the sheer scale of modern computing demands higher level languages and big teams to work on them. There is no way of writing assembly code for an NVIDIA GPU because they don't release you could arguably say that shader code is perhaps compiled to assembly. There's not really a way of writing that sort of bare metal stuff on a modern GPU because there cannot be. And I think that, or perhaps there could, but it would be very cumbersome. It's one of the things that makes me look at the entirety of modern software development and say that things have changed, and it's not necessarily a bad thing, but it's certainly changed the way things work, and I think that requires people to rethink more than sometimes they do.
Let's just look at the timeline. I was talking about exponential change a minute ago, and there's no better example than to look at the timeline of computing. And when I was born back in the Cretaceous period, the state of the art in school classrooms in the sixth form was a slide rule. And that, for anyone who's never seen it, it's a piece of wood or metal that's got a sliding inner part and a sliding cursor, and it has logarithmic scales. So it means you can do multiplying with it to limited precision, but close enough to get you, within something that's useful. And engineers used to use this. NASA, Boeing. These were universal for 340 years after it was developed, until the mid-70s. And then in 1972, the Hewlett-Packard HP35 scientific calculator came out. And this, or was it the HP25? I should know, I've got one. But it would do like scientific calculations. You could do exponents, you could do logs, stuff like that. That had 18,000 transistors in it in 1972. The current iPhone has approximately 20 billion transistors. And at the same time, this is what NVIDIA described as today's basic unit of compute. A data center, typical data center full of the latest NVIDIA GPUs, will have 10 quadrillion transistors in it. That's 10,000 trillion transistors in one building, which, of course, is at everybody's disposal via the cloud, although not exclusively, of course. But if you're wondering how it is we're able to do things like AI, have things like ChatGPT, and have it do so much, it's multimodal. They work on images, they understand images, they can generate images, and they work with text, and they can reason to a high degree. We're approaching PhD level now. And the reason we can do that is it's because of scale. 10 quadrillion is obviously a much bigger number than the 18,000 in the Hewlett-Packard calculator. But it's not stopping there, because the algorithms are being improved as well. And you're getting probably a factor of 2 every year in algorithmic efficiency. And of course, we're approaching the stage where AI will be its own researcher and developer. And at that point, all bets are off, because that's just going to accelerate so fast that from our point of view, everything happens almost instantaneously. And of course, that's what's called the technological singularity. So these are huge numbers, but it is sobering and fascinating to think that all of this is because of GPUs, and GPUs started because of the games industry.
There's a certain thing to talk about here, in as much as one of the issues that attends this is that GPUs are arguably what we might call vector computing, or sort of single instruction, multiple data stuff, which also appears on other sides of CPU. it's one of a few different approaches to doing computing that have come up since the mid-90s. Which you talk about conventional computers for a long time have used Intel stuff, which we might think of as complex instruction set. Then you've got the PowerPC 600 series that were in the early to mid-90s, which were reduced instruction set. You've then got parallel computing and intermediate things like VLIW, which I think like Itanium. Intel's recently cancelled CPU line, which was supposed to be an alternative to and perhaps eventually a replacement for the x86 series. But even x86 series CPUs now are not really running x86 instructions. They emulate internally an x86 processor because it's much easier to make a little processor that emulates very quickly an x86 rather than make an actual x86 core. These are all just examples of doing things differently in computing. GPUs are a single instruction multiple data thing. We take large data sets and we run the same mathematics on all of them. It's fundamentally what shaders do. That's probably, you could probably call it RISC, but more to the point, it's a single instruction multiple data thing. It's what we call vector processing. It's pretty much the only one of them that's really caught on. You could say that RISC has caught on because ARM is very big, but then there's some arguments about how you define what RISC really is. It's one of the couple, let's say, of really successful alternatives to the dying of Moore's law, when we had this idea that the number of transistors would double every so often. That remained true. The problem through the end of the 90s, the early 2000s, was that was causing us to have more CPUs, not faster CPUs. And one of the things that we've had to do, where I'm going with this idea, one of the things we had to do between then and now is figure out the best ways to make use of multiple cores, from a couple of dozen cores on a CPU to thousands of cores on a GPU. Writing the code for those became a big challenge in computer science, a big challenge to people who write software, engineering tools, compilers. And there's been some interesting stuff in the games industry in the meantime, because Sony came out with the PlayStation 3 with the Cell processor, which had 8 cores, which was actually bought up in large numbers by certain organizations to do defense and research projects because it had this multi-core architecture. It was notoriously difficult to write code for. So was the Saturn, I believe. They were notoriously hard to work with because we hadn't really figured out some of these things. And the entire Itanium line never really worked properly. It never worked in the way that it was intended to, and was only kept in production for a long time by the fact that some company wanted it and was willing to pay Intel to keep making it. Because it turned out that they had some new ideas about how to do computing that sort of didn't work very well in practice. The compilers required to do it, the tools required to do it, turned out to be sort of impossible to write. And a lot of this stuff, going all the way back to the beginning of computing and up through gaming and Commodore 64s and things, comes from the fact that we had to go through these not so great things to get to the great things. And so it's the space shuttle gambit. The space shuttle was never a great space transport system, but it kind of showed us what not to do.
It's almost a Darwinian thing, isn't it? You've got to have, you've got to have some failures to, highlight the successes. Just a matter of interest. I've been doing some calculations here. We were talking about Moore's law, the idea that the number of chips on the number of transistors on a chip would double every 18 months or 2 years. Well, there's a slight statistical consensus that AI is currently doubling every 7 months. Now, if you work it out, that represents in 1 year 3.3 times the power in 1 year. If you compound all of that, in 2 years, that's a 10 times increase in AI. In 5 years, it's a 380 times increase. In 10 years, it's 145,000 times increase. And in 20 years, I know what you're going to say, Phil. In 20 years, it's 21 billion times in 20 years. My view is that that's conservative. I think it'll accelerate. Phil's going to tell us that we're going to run out of power.
Well, we're literally going to run out of mains power at the wall before we get to that point. And I think that, you can talk about quantization and reduced precision models and so forth all you like. I think that there's a couple of things that concern me about AI, which we probably talked about before, but it's worth reiterating. It's not clear that fixing the problems that it has, like its ability to be enthusiastically wrong all the time, which they absolutely are, it's not clear that that's not going to take an exponential amount of power, both in terms of the number of tensor cores you need to run these things and the amount of electricity they consume. I think that there are going to be some practical limits before we see several 100,000 times in 10 years. I don't think that's going to happen. I think big things will happen and have already happened. But we seem to have been hovering on the cusp of something. Through the 90s, anyone who lived through the 90s and played video games in the 90s and had Commodore 64s and Amigas and then 3DFX Voodoo series graphics cards and then NVIDIA graphics cards saw huge regular improvements. The video games you played got better every 6 months and it was visible. And every year you bought a new PC or every 18 months, it was blatantly clear. Yeah. They look better. Although whilst we're talking about video games, I looked this up the other day. And I can't remember exactly what the numbers were, but, I think it was 1999, between summer 98 and summer 99, somewhere around that point. We had Deus Ex, Diablo 2, System Shock 2, and a couple of other titles that anyone who's played video games will remember to this day. If you look at what was released in the last year to summer this year, it's like Animal Crossing or something in terms of the most popular game. I think standards have slipped, but maybe I'm just being a real old guy.
That, all this advancement, it's a bit like films. I think, the technology has allowed much more realistic environments to be generated, and now the environments are so complicated they generate them procedurally. But the creativity has certainly, I think waned. I mean, I was looking at some of the top games that are available now, and they're just sequels to the same titles I was playing when I first, was using the original Xbox. You've got Call of Duty and all those games, and I'm not entirely sure that they have really, gone all that much further than even Wolfenstein or Doom in terms of your general gameplay, other than the introduction of worldwide multiplayer modes and communication methods.
I mean, I don't want to get sort of sidetracked into talking about video game in too many specifics, because I think that's the video games are of interest because they have provoked all this technological development. In terms of what's big now, people are making most money out of things like Candy Crush. It's not hardware specific. Mobile gaming. I mean, bear in mind, these things are as reliant on GPUs as anything else. The idea that the CPUs CPUs wouldn't be 10% fast enough to render what a modern phone or games console or PC can do. But in terms of the actual content that's going into these things, we have an embarrassment of riches as regards rendering capability. And then we have, nothing particularly interesting going on.
There's almost a physical law, though, in improving computer games, which is that if you talk purely in terms of detail, if you're going to create assets which are increasingly detailed, they're going to take increasingly more work. And of course, we have better tools to do that, and AI will probably give you a productivity increase measured in the thousands once it becomes controllable and reliable enough. But it's also in terms of interactivity. One of the reasons, do you remember when we used to have a format called CD-I or something like that? And, this was going to be the new mass medium, interactive CDs, which weren't just audio, they had video clips on them. And they were quite entertaining for the first 5 minutes. But if you imagine they became more and more capable, it's like each one of those would become as complex as a video game, because you have to account for every possible choice, every possible outcome. and it hits a fairly soft but immutable barrier where there just isn't the money or the resources to take it any further, and that doesn't change whatever the level of technology. That's just counting.
Oh yeah, I mean certainly a big video game will cost more than a movie to develop these days. Long gone are the days when you would know the person who designed it. You used to have names like Archie McLean and David Brabham and people like that. And nowadays it is about, you've got a guarantee to make your money back.
Yeah, and the credits take about 20 minutes to roll. At the end.
In modern video gaming, I really feel like an old guy when I say things like this, but I think video games have gone way off the boil. But it brings me back to things like Cyberpunk 2020, which is a recent one, which is an interesting case in point because it was among the first to show off things like the ray tracing that we were talking about earlier. And it's not all that great. There are many things about it that are good. Functionally, what ray tracing in video games in its original application, we're talking about this hardware being used for all kinds of other things, but in its original application, the ray tracing gives you the ability to see things reflected that are not on screen. Because ordinarily, if you look at a flat piece of concrete with a door at the end in a video game, you will see a reflection of the door in the puddle of water that's on the concrete. If you start to tilt down the camera, you'll see it will cleverly do some sort of, ripply water effect or sort of fade out the bit that is no longer being rendered on screen because it's doing the old trick of just taking the rendered flat object and flipping it upside down and putting it on. And you'll always see that there's never like flat floors in video games. They always have like a rippled marble effect on them, like a sort of polished floor, because then you don't quite see the cludge. You don't quite see the fact that it's not really a reflection. Now, ray tracing will give you a reflection. So it's actually looking to bounce off the water and somewhat accurately simulate the bounce of light, as Dave was saying. It's still quite hard work, even with the most modern gear. That's still quite hard work. And certainly in a Cyberpunk, you get these weird effects on the top of cars when it's pretty obvious that it's kind of kludging it and doing some sort of ray tracing, but it's not quite happening at full frame rate or full resolution, and it's not quite being updated every time the car changes its orientation with respect to the world. The idea that modern GPUs do ray tracing, they will, but it's not like you just turn it on and every light source in the scene is being ray traced in real time. That is not they will not do that. That's not possible.
No, I guess AI interpolation could also be used with the frame rate as well.
Yeah, my understanding is that's what it does, but then you look at the reflection of the world on the top of your highly polished car, and it's a little bit on the sort of side. It's not. I don't think it was that successful, to be honest.
Yeah, so I mean, it's gaming. This kind of tech, though, that's it's obviously made special effects in films. It's crossed over into that sort of sphere, hasn't it, and made the development of that much easier than it ever was, and unfortunately is seemingly used in every single film for every single frame. But so I think we're coming to 3/4 of an hour, so I think we've discussed quite a bit.
Well, the only other thing I wanted to say was that in terms of video games, we did break a barrier a little while ago. And the barrier was that, like, certainly people of my father's generation, he's in his 80s now, looked at the stuff that was being done in the 80s, which was, little blobs of colour that moved around the screen and the stuff that, not even sprites. And we're talking about the really early stuff where they didn't have sprite hardware. And then the stuff that came up through the mid-90s, which was, the sort of Sonic the Hedgehog and stuff. You had to like the aesthetic to be into it. Now you can look at the first level of Sonic the Hedgehog on a Mega Drive, Saturn, Genesis if you're in the States, and say that's pretty and it looks nice and it's nicely designed and it's green and blue and it's all nice and pretty. You have to like the aesthetic. It's a very low resolution, 320 by 200-ish display with about 32 colors on it. It's 64, I think, on a Genesis. You have to like that in order to enjoy it. These days, about 10, 15 years ago, we passed through a barrier where it started to become more possible to render something that looked good enough that it was acceptable to the general audience. You don't have to be a video game fan. You don't have to like a certain fixed aesthetic that's forced upon you by the hardware. You don't have to like that in order to enjoy a video game anymore. And I think that's one of the reasons that there's been such an explosion in popularity, because it's become a little bit more like being immersed in a movie. And that's something that they always wanted. The cover art on video games always wanted you to think that you were about to be immersed in a real-time movie of your own making. And it was never true until relatively recently, when you can sort of look at some of the recent Tomb Raider games and go, holy God, that actually looks better than the most recent Tomb Raider movie. She looks more like Lara Croft than the woman who played Lara Croft, which is quite shocking, actually. And I think that has come from the hardware. But now really what's most interesting about it is, as we've said, what other things come from that same hardware. And I think that's been underpinning quite a lot of the things we've been discussing on this podcast week after week.
And just a nerdy point of view, you've just taken me back to the days when I used to be attempt to design games, when I got to know how to manually do dithering on the image, because I knew how the CRT display would show it. You wouldn't see the dithering so much on a CRT display because it smoothed everything out, so you could make graduations of color. But anyway, on that note, I think we'll leave it there for this week. So thank you, Dave and Phil.
Yeah, thanks. See you next time.